In this video, I'm going to talk about logarithmic scale, which is one of my favorite things because it applies so much in the world of technology that we live in today. Logarithms do a very good job of taking data that grows exponentially fast and turning it into visualizations that are easier to use for predictions. A log scale counts by powers of 10, not intervals of 10. One of the famous examples of this logarithmic scale is what we call Moore's law, which says that the number of transistors in a dense integrated circuit doubles approximately every 2 years. Now, if you've ever seen Moore's law, you've probably seen the graph on the right, which on the x-axis shows us the time in years from 1971 to today, and on the y-axis shows us the number of transistors in a dense integrated circuit. And it goes from 10,000 to 100,000 to a million, 10 million, 100 million, 1 billion, and 10 billion. And those are the equally spaced lines. Now, that's a log scale. And on a log scale, Moore's law looks delightfully linear. And we can see a very nice pattern of linear increase. But if we used a regular linear scale instead, we would be counting up to 20 billion, going by 5 billion, 10 billion, 15 billion. And in this linear scale graph, we can clearly see the exponential nature of Moore's law. But it is very difficult to actually figure out what any of those values are on the scale because it's an exponential function that is almost completely flat in this scale until you get to the years about halfway between 2000 and 2010. And then it just blows up from there. Exponential functions are very hard to see when they grow this much. Another famous log scale graph is the microprocessor clock speed in hertz between 1976 and the current year, or in this case, 2016. If we look at the graph with the log scale, we see on the x-axis the years between 1976 and 2016, and on the y-axis that log scale goes 10 million hertz, 100 million hertz, 1 billion hertz, 10 billion hertz. So we're multiplying by a factor of 10 with each evenly spaced line. On the left graph, if we looked at this with a linear time scale or a regular scale, our evenly spaced lines would be something like 5 billion, 10 billion, 15 billion, 20 billion, 25 billion. So we're counting by 5 billion each time. We're adding 5 billion each time, not multiplying by 10. And in this case, we can see the exponential nature of the graph. But again, between 1976 and about the year 2000, it basically just sits on the x-axis. There's almost no vertical movement in this graph because it's growing so slowly compared to its later growth. Right? So again, this is an exponential function that just kind of blows up if we look at it in regular scale with almost no ability to read the data points. But in log scale, it does look roughly linear with a little bit of variation. This one's not quite so nice as Moore's law turns out to be, but you can definitely tell what the data values are a little bit easier in this scale and see the linearity of the graph with a log applied. Now, for any quantity that's experiencing what you believe to be exponential growth, it may make more sense to graph it in a log scale so you can see the growth a little bit better. To graph with a log scale, you have 3 options. The first option is to use software that can build a log scale, and in this case, Desmos does not have a log scale option, so that's out of the question. We can also use graph paper that has a log scale on the appropriate axis. There is log linear graph paper, there's log graph paper, and of course there's linear graph paper, which is just your normal graph paper. The third option you have is to just transform the data to reasonable values for a linear scale. And we do that by taking a logarithm, and that's exactly what the pH scale and the Richter scale do. They take the log of hydrogen concentration to make it a more reasonable scale, and it takes the log of the amplitude of the Earth's motion in microns to make it a more reasonable scale for us to talk about. When we look at log-scaled graphing paper, there are 9 unevenly spaced markers between major grid lines, and these count the multiples of the lower major grid line. For example, on the first set of grid lines that we have here, the x-axis is counting from 0 to 7 evenly spaced, counting up 0, 1, 2, 3, 4, 5, 6, 7. The y-axis counts 100, 200, 300, 400, 500, 600, 700, 800, 900, 1000. So it looks like we're adding 100 each time, but those are not evenly spaced values anymore. So the space between 100 and 200 is the biggest space, and then 200 to 300 is the next biggest space, 300 to 400 is the next biggest space, and of course that means that the space between 900 and 1000 is very, very, very small. So these are not evenly spaced markers. What I'd like you to do is try completing this scale on the second and third examples here. So same X scale, 0 to 7, counting by ones. The Y scale of the next graph goes from 1000 to 10,000. And then the third graph goes from 1 million to 10 million. So go ahead and start by trying to just plot the scale on that y-axis. Pause the video, give it a try. Okay, we're back. Let's see how you did. The unevenly spaced markers between the major grid lines should be multiples of the bottom major grid line. So the bottom major grid line here is 1000. So if we're using multiples of that, it should be 2000 for the first unevenly spaced line, 3000 for the next unevenly spaced line, then 4000, 5000, 6000, 7000, 8000, and 9,000, that line really close to the top, really close to 10,000. Okay, for the third graph, we started with 1 million, so we want multiples of 1 million. So 1 million, then 2 million, I'm just gonna write 2 MIL, then 3 million, 3 MIL, 4 million, 5 million. Remember, these are not evenly spaced. 6 million, 7 million, 8 million, and this line really close to 10 million is 9 million. All right, so this is a case where you really need to have the graph paper. To do this by hand is really, really difficult. What I'd like you to do next is to pause the video and try plotting the points that are listed here. I'll go ahead and plot them for you when you come back, but do give it a try because it is trickier than you think it's going to be, and watching me is better if you're able to correct any misconceptions you would have. So give it a try. Okay, we're back. Let's try. We'll first plot 1, 170. So 1, 100 is on a grid line. The next minor grid line would be 1, 200. So 1, 170 would be somewhere closer to the top between 100 and 200. 2, 950. 950 is going to be between the uppermost minor grid line, which is 900, and the next major grid line, which is 1000. So I'll just put a 950 between those two vertical values. Next, we'll plot 3, 1400. And I can't do that on the first graphing plot I have because I can't see where the next value is. So let me switch over to the middle plot here. So 3, 1400. 1400 would fall between 1000 and 2000. It's really tempting to start counting up and go 1000, 1100, 1200, 1300, 1400, but that is not how this works, right? So it's 1000 and then 2000 for the first minor grid line. 1400 would be a little bit below the middle of this, so 3, 1400, maybe about there. 4, 8200 would be between the 8000 and 9000 minor grid lines. So 4, 8200 would be just above the 8000. 5, 1,200,000. Let's jump over to that last graph now. 1,200,000 is going to be between 1 million and 2 million. So between the major grid line and the first minor grid line. So 5, 1,200,000 is close to the bottom there, closer to the 1 million than the 2 million. And finally 6 and then 5,500,000 would be between 5 and 6 million as the minor grid lines. So 6, and then 5,500,000, somewhere around the middle of that. Now I've got one for you to try. The data we've got here relates the number of human genome base pairs that could be sequenced for $1 US in every year. So every year, the $1 you spend goes farther to sequencing human genome base pairs. This starts with 189 base pairs sequenced in the year 2001, then 274 in the year 2002. We're going to count by 1 year each time. So 383 base pairs in 2003, then 821, then 1,131, then 1,557, 2,085, 30,930. That's a big jump there. Then 636,213, another big jump. Then 2,599,222, then 6,438,325, 13,755,903, 16,329,937, 18,400,824, and 33,321,408. If we just plot this data using a linear scale, it doesn't look very easy to understand. So if I plot it with the years since 2000 on the x-axis, so that's counting 1, 2, 3, 4, 5 up through 15. And then on the y-axis, I'm counting evenly spaced 20 million and then 40 million. Between 0 years after 2000 and about 8 years after 2000, we can't even see the data. It's just washed out into the x-axis. And then we start seeing data after that. This isn't going to work on a linear scale for us to be able to read this data. So let's go ahead and look at this data on a log scale. It does look like it may have some exponential properties here, although not as smooth and nice as some of those other graphs. Let's go ahead and try to plot this data. I think this would be a great time to pause the video and give this a try yourself, especially because you're probably going to want to spend some time counting values as you go and marking off some values. So give it a try and then come back and let's do it together after that, and we can see how your data plotted. Okay, we're back. Let's give this a try. I'm going to start by making the time column next to the year column. So 2000 is time 1, 2002 is time 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Do note that on the x-axis, on the graph I've given you, it counts by twos, which means that year 1 will fall exactly halfway to 2, and year 3 will fall exactly halfway between 3 and 4, etc. Okay, not exactly on a grid line there, so I thought I'd point that out. Okay, so in year 1, we have 189 base pairs. So that's, if I'm counting up by multiples, that's 100, then the next minor grid line is 200, then 300, then 400, etc. Year 1 would be 189, which is between 100 and 200, and definitely closer to 200. Year 2 is 274, which is between 200 and 300, closer to 300. Year 3 is 383, which is between 300 and 400, closer to 400. Year 4 is 821, and I'm going to zoom in. This is where I have an advantage over you here. I'm going to zoom in so I can see the 900 line and the 800 line very closely. And 821 is going to be a little bit closer to the 800 line. So I'm going to plot that point. All right, what comes next? Year 5 is 1,131. So year 5 would be here. 1,100. Well, if I'm multiplying 1,000 now, the next grid line up would be 2,000, then 3,000, 4,000, etc. So 1,200 would be between 1,000 and its first minor grid line, much closer to the bottom grid line of 1,000. 6, 1557. Again, it's between the same two there, closer to the middle. 7, 2,085. So 7 is going to be just above the 2,000 grid line, that first minor grid line. 8, 30,930. So 8. Now 30,000 is going to be between 10,000 and 100,000. The first grid line up would be 20,000. The next grid line up would be 30,000. These are minor grid lines we're talking about. And I need to plot almost 31,000. So 31,000 is going to be very close to the 30,000 at a value of 8. This is a significant jump in the graph. It kind of seems like a mistake. Just note that up to that point, if I grab my ruler here, up to that point, we had a pretty decent linear trend. I'm just going to pencil it in here. A pretty decent linear trend here on the graph. Something like that. All right, what happens after 8? Year 9, 636,000. So let's see, I need to zoom in again for year 9. Year 9 is going to be halfway between 8 and 10. And I'm going to zoom in to the section that's between 100,000 and 1 million. So I need 636,000. Going up, this would be 200,000, then 300,000. I'm going to touch them now. That's 400,000, 500,000, 600,000 is right there. 700,000 is there. So it's between these two tick marks. And that's going to be 636,000, so right about there. Erasing all my little marks now. Whew, that's hard to graph. Okay, 2010, year 10 would be 2,600,000. So again, 1 million, between 1 million and 10 million, we would next count 2 million and then 3 million. So this is going to be a number between 2 million and 3 million, a little closer to 3 million. Then 6,400,000-ish. So this is 4, 5, 6 million is right there. So a little over that. 12 and 13, almost 14 million. So 12 and 14 million. Well, this would be 10 million, then 20 million, then 30 million. So 13.7 million would actually be very much closer to the 10 than the 20. So maybe we're out there. 13, we have about 16 million. So again, just between 10 and 20 million, just a little higher. And then 18 million in year 14, again, just a little bit higher. And then 33 million, a big jump, would be up to between the 30 million and the 40 million line. Whew. Okay, so if we take a look at that, we had a very nice linear looking graph in the first maybe 8 years, and then a huge jump in the graph. And then we may actually have some linear behavior here happening again now that we've had that huge jump. Looks like we get kind of a best fit line there about like that, but definitely a big change between about the year 2007 and the year 2011. Notice that we can see this change in the log graph. Whereas when we looked at this in the linear graph, it was all just points on the x-axis.